Okay, great that everybody's back. And we will continue with network function insertion.
Good afternoon, everyone. So today we are going to talk about network function insertion support that we recently added in OVN. My name is Shraddhara, and I have here with me my colleague Naveen. And there are two other contributors, Karthik and Aditya, and we are all from Nutanix. So, okay, let me start with the objectives. So OVN is already quite feature-rich when it comes to general packet forwarding capabilities. But still, there are several scenarios where we need to integrate advanced set of features that are offered by established third-party vendors, right? And that's where we need to support the ability to redirect traffic through a virtual network function. Now, oops, sorry. Oh, I can't go back. Okay, this is a laser pointer. Nope, back. Yeah, okay. So secondly, we need to have the ability to redirect only a subset of the traffic based on packet classification. Third, we need to make this redirection stateful. That is, if the request packet was sent to the virtual network function, even the response packet of that connection needs to be sent to the same virtual network function. Then we want to support it for both overlay and VLAN networks. And the VLAN network has its own challenges, as we'll see later. And then from the get-go, we wanted to make this solution resilient and scalable, right? So if one network function instance goes down, we should automatically fail over to another instance. And scalability perspective, we wanted to do active-active load balancing across multiple NF instances. Now coming to the mode of operation. So first the inline. What inline indicates is that we redirect traffic to a network function, and then after processing, it comes out of the network function and it continues on its journey. And one important point to note is that what we support is the network function in a bump in the wire model. That is, it won't modify packet header as it traverses through it. Now, what we have upstreamed and what we are today going to talk about is mainly this inline mode. But we do also, as a future work, want to take up VTAP mode, where we basically clone the packets and redirect to the network function while the original packets continue uninterrupted. Right. So now let me start with the overview of the solution. So first, the entities involved and how they relate to each other. So first, the network function entity. So network function is represented by a pair of logical switch ports. As we can see in this example, this NF1, it has NFP1 and NFP2. One is input, another is output. So traffic is sent to one port and it comes out of the other port. Then in order to support HA and scale out, we introduced another entity, which is network function group. So here the NF1 to NFN, all these network functions are grouped under an entity that is NFG1, right? Now, where is this network function applied? So network function is applied at a logical switch level, and it is associated to an access control list, right? So in an ACL where we today specify priority, match, action, now you can also specify an NFG there. What effectively happens is any traffic matching that ACL will be redirected to the network function. Now, which network functions can participate? That's where health monitoring comes into the picture. So we have added support for a pass-through health monitoring. So where OVN controller sends probe packets to one port of the network function, and it monitors if the same packet is coming out from the other port. And based on that, it marks the NF as active, online or offline, right? And only those which are marked as online can participate in the traffic path. Now let's take a look at the logical view of the packet flow. So let's assume that this port P1 is part of a port group, and to that port group we are applying an ACL, and that ACL has an NFG, right? So first, let's consider the from L port ACL, that is the outbound ACL. So any packet coming out of this P1 it does an ACL match in the ingress pipeline, right? And if this ACL has NFG in it, let's say this NFG1, then the packets will be redirected to the import of the network function. One of these network functions will be chosen, one of the online network functions. And at the same time, that identifier of that NFG ID will be committed in the city entry of this P1's city zone. Now the same packet after processing comes out of the other port of the NF1 and it continues on its journey, right? So the blue arrows represent the request path. Now let's talk about the response, which is represented by the green line. So the response is destined to P1's MAC address, right? So it will come here, and when it does the egress processing of the logical switch, there it does a city lookup, right? And in I mean, the city lookup is already happening, but now we fetch the network NFG ID that was earlier committed from the city entry, and based on that, the packet gets redirected to the output of this NF. Right? And when it comes out of the other port, it gets delivered to P1. So that is how the from L port ACL will work. To L port ACL is similar, just the roles are reversed. In this case, green represents the request. So when the request packet comes destined to P1, in the egress pipeline, ACL lookup happens. And the NFG ID is read from the ACL, packet is redirected here, and the CT entry is committed. And the response similarly in this case, as it goes out, it looks up the city entry here and redirects. So essentially, in summary, in either case, during request processing, the ACL lookup happens, and based on the NFG ID, the request is forwarded to the NF. And at the same time, the CT entry, the NFG ID gets committed in the CT entry. And during response processing, we read that NFG ID from the CT entry, and thus we forward the packet to the network function. Now, a little bit about the HM mode. What I was just now talking about is active standby, that if it so happens that there are multiple NFs and all are in, or most of them, many of them are in online state, then we choose one of them to participate in this traffic flow. And this is what we have so far upstreamed, but we also will be adding support for active mode, where the packets will be load balanced across all the NF instances. Okay, now what happens in case there are multiple logical switches, right? What I was just now talking about, you applied ACL to a port group, but the port group has member ports which are in different logical switches, let's say LS1 and LS2. Now, that would mean that we have to apply the redirection rules in both the logical switches. Not only that, the NF itself has to have ports present on all these logical switches. Now, it is impractical, or it is not scalable for the NF to actually have, let's say, the NF VM to have multiple pairs of such VNICs just to cater to all these different logical switches, right? So this is the alternative approach that we came up with. So what happens is, when the NF VM, let's say, is deployed, the CMS would attach these ports to one LS. Let's just call it service LS, but it's not any special LS, just regular LS. But let's say it uses this LS for hosting these NFs. And it will create a NF entity using NFP1 and NFP2. Then it will create an NFG, and then associate that NFG to a ACL. Now, at that point, if let's say this ACL is applied to a port group, it's the CMS's responsibility to see if these port group members are present on which LSS, and then go and create child port of this NFP and NFP2 on each of these logical switches. Right? In this example, it created child ports of NFP1 and NFP2 here. Similarly, it created here. If another P3 gets added in another logical switch, CMS has to create child ports there. And when NOD installs the redirection rules in each logical switch, it uses the ports that are present there, whether it is child port or parent port. Okay, now coming to the case, let's take a look at the cross-host traffic. So now, okay, so here I'll focus mainly on the VLAN network, right? So let's say this is VM1, it has port P1 here. And this is where we are applying our access list with network function. And this is NF, which is on a different host, right? Now, as the packets enter from P1, here they get classified, and the output is set to, let's say, NFP1, which we saw just now, right? Based on ACL classification. Now, if it simply sends that packet out into the physical network at this point, the packet redirection will actually not happen, right? The decision taken here is irrelevant for the physical network. So what is needed to be done is that it needs to tunnel this packet to the other host, right? For overlay network, it's not a concern because anyways it is tunneled. But for VLAN network also, now we need to make sure these packets are tunneled to the other host. And after that, the packet is, let's say, delivered here. Now, when it comes out of this other port, at this point also, we cannot just send the packet to the physical network as it is. That's because then the physical network will learn this P1's MAC address from host 2. We don't want that, right? So there also, it needs to be tunneled back to host 1. After reaching here, it can go wherever it was originally meant to be, right? So this is the intention. Now, how are we achieving it, right? So let's say the packet comes out of this port. Here, the logic is that based on the destination, the output gets set to NFP1, right? Now, the logic here is that if output is a port of type NF, then we tunnel, and it is not local to this host, we tunnel it to the host where this NF is located, right? So that's the logic that's implemented here. Now, upon reaching here, the inner packet of from the tunnel is sent to this port, right, to the NFP1. But at the same time, we also commit this tunnel interface ID into the city entry here, the city entry in NFP1's zone. There in the city label, we are now committing the tunnel interface ID. Now, once the packet comes out of the other port here, now at that point, we do a lookup into the other NFP1's city zone. Even though the packet is coming out of NFP2, we have a linkage between these two ports. So we look up into the city zone of the NFP1 to retrieve that tunnel interface ID, and using that, we are tunneling it back to host 1, right? So that's how this solution works. Now, and after that, it just inner packet is sent to its original destination, right? Oops, sorry. Oh. Now, if it was the other direction, that is, if the packet was coming from outside, it would be very similar. So there we will, again, it is decided that, okay, it has to go to this other host. So it will be tunneled to the other host. And there also, again, it will enter it's just follow the reverse path. It will be forwarded to NFP2 in that case. And the city entry here, we will commit the tunnel interface ID. And when it comes out of NFP1, it will do a city lookup in NFP2 to retrieve that tunnel ID. And using that, it will send the packet back to host 1. And then the inner packet will be delivered to P1, right? And yeah, so that is how it happens for cross-host traffic in case of VLAN network, which means that we have to, even for VLAN network, we have to make sure the MTU is set correctly to accommodate this additional tunnel header, right? So for overlay subnet, it is just shown here. Here, there is no such, I mean, it is anyways tunneled. So it just comes here and then continues on its journey, right? This processing is specific to VLAN network. So yeah, at this point, I'll hand over to Naveen. Go through the implementation.
Yeah, thanks, Rigdara. I'll walk you through the implementation part of this feature. Right. So following are the NB changes and SP changes added for this feature, right? Like as in the previous slides, like there was explaining, right? Like now ACL table schema is updated to refer to network function group or NFG, right? So NFG itself is a new table, so that we have added, so which has a unique identifier like from 1 to 255, basically uint 8, and the mode of insertion currently it is inline, and the list of network functions that this is referring, right? And then what is the current if there are multiple network functions, what is the current selected active network function, right? That is persisted here. And then if all the network functions of this NFG went offline, what is the fallback method that we have to take? Either it's fail close or fail open for the traffic, right? And network function is what referred by NFG, right? A network function itself is a set of logical switch ports, right? Yeah, I mean, in this case, we are calling it as input and output, and it is referring to NF health check table, right? Like to decide whether a network function is online or offline. So network function health check is a new table that we have added. It is similar to load balancer health check, right? Like we have extended load balancer health check service monitor infra to support health checks for network function as well. So it has interval, timeout, success count, failure count. And the ports LSPs, right, that are referred in network function, right? Those are network function ports, like to say any function, any LSP as network function port. So we have added new parameters. Example is NF and NF linked port to to configure the peer port, right? And for these ports, we don't want to receive any multicast or unknown unicast packets, right? Like we don't want flooding on this. That's why this the receive multicast flag is added, and then we don't want to learn any FDB entries on these ports. That's why this one more flag is added to disable that, right? And for to support health check, right, we need source like source IP, source MAC, dest IP, dest MAC, right? Like so today at NB Global, we for load balancer there is already service MAC, which is common for all the health check packets. So apart from that, we have added three dest MAC and source IP and dest IP. So these are as of now it's NB Global level for NF health checks, right? These IPs and address MAC addresses are used for probe packets. And coming for SB, yeah, we have extended this service monitor table, which is already there to support NF. So with these fields like type, what is the source MAC, the MAC refers the source MAC, and then the logical input. Yeah, so these are the new stages that are added. ACL, sorry, in the both ingress and egress pipeline, network function stages are added, and there are few other stages which are updated. Right? So this is a sample configuration, so which is creating a set of creating NF ports, two NF ports, and then creating NF with those ports, and then we are creating a NFG, which refers to this NF, and then finally we are creating a VM port, which is P1 in this case, on which we are applying ACL, and that says redirect the traffic to the NFG. Right? So this is a simple example. And so let's walk through high level through the logical flows, right? So this slide represent in case of outbound traffic, like which is like from port, right? From port ACL. So how the flows looks, right? In the ingress ACL evaluation stage, if it has NFG, right? The stage will store what is the NFG ID and some flags that says, okay, this packet now needs to be redirected to NF, and this is a like request direction, right? Origin direction. And then in stateful, whatever the information we stored in the previous stage, so we are committing into the CT label, right? Like we mark this connection as NF connection, and then what is the NFG ID, which will be used in the egress pipeline. Right, and then in the network function, this is a new stage, which is actually redirecting the packet to the network function port. This is where we overwrite based on the previous registers values set. Right, like we will match based on whether network function bit is set, it is origin direction, and then accordingly output. We are overwriting the output here to NF P1. Right. So now the packet is redirected to NF. Right. Yeah. So now, now for let's see the response packet, right? Now when the response packet is coming, so it will hit the in the ACL evaluation stage. So we already for the existing connections, right? We load some information into the registries. So now we load this NFG bit as well, network function bit is set. So accordingly, in the output out network function stage, So we know, okay, this is a network function packet, and this is the in the CT label, whatever the NFG ID we are storing, we'll check. Okay, accordingly we'll figure out the output. In this case, it has to go to the NFP2 because request went to NFP1, response has to go to NFP2. Right, and then since we overwritten the port in the egress pipeline, we have to re-inject the packet back to the ingress pipeline. So this is what it is doing. It is re-injected back. Once the packet re-injected back to the ingress pipeline, before re-inject, we are setting a flag here that okay, this is re-injected. So we are using that flag regate 23-bit, and just we'll do output. So from there, it follows the regular pipeline. Right now, once the packet processed and comes back, right, in the from the NF, right, before redirecting, we already evaluated some egress stages, right? So we want to skip all of them. So if the packet is coming from this NFP1 now in the egress pipeline, we'll skip those stages and we'll re-inject. I mean, we'll jump directly to the table 12. So for inbound, the rules are similar. It's just like opposite. I'm in the interest of time, I'm skipping. Right. So yeah, as for the cross-host traffic, as Regdara explained, right, like this is applicable only for VLAN, right? Like on the host one, so these are the flows in the remote output table. Yeah, like if it is a VLAN network and all, if it is the packet has to go to the NF ports, we are adding the rules to tunnel. And in the host two, when the packet reaches here NF, in the table 0 physical to logical table, we are storing the tunnel ID and we pass it to the logical pipeline, egress pipeline on host 2, so that it gets that information gets committed, the tunnel ID gets committed to CT. And once the packet comes after processing, let's say from NFP2, right? So we need to like we'll do lookup on the pair port zone, and then the information is so in the table 43 local output table, we do look up on the pair port zone and we restore the tunnel. I mean, we'll again find the tunnel ID, and then we'll again tunnel back the packet to the host one, right? So yeah, so for the health monitoring, right, this is all the existing infra. So so OVN controller is doing distributed health monitoring for load balancer. We have extended it to do for network function as well. Only the controllers, I mean, only the hosts on which NFVM is hosted, those controllers will do the probing. And the addresses for those packets are picked from these options, right, for probe packets. And OVN, like for NF, it's only ICMP echo request is what we support, the controller supports today, because it's pass-through probe, it sends ICMP request and expects the same packet should come on the peer port. Right, as long as that's happening, it marks the service as online, otherwise it will mark as offline. So yeah, coming to the availability, so one based on the service monitor table, whatever controller updates, so North3 is listening on that, and then if so in the first diagram, right, all are healthy, right? So in active standby mode, North3 will select the first like let's say first one in the list as active, and then the packets will be redirected to only active network function. The flows are updated accordingly. In case if something like NF1 is marked as offline by controller, it will update the flows to select to NF2. Right? And if both are down, right, both are offline, so then the fallback method kicks in, which says whether the packet has to fail open or fail close. And the future work, we want to support VTAP mode, in which case there is only one port assigned to NF, which is like, and all the packets will be cloned, the request or response packets, and then forwarded to the NF. Right. In the interest of time, I'm skipping the schema and all. Right. In case of active, so the plan is to support multiple network functions to be in active mode, so that the load can be distributed. Right. Yeah, that's it. Thank you.
Thank you very much. I'm not sure if we have any time for questions. Then let's do one short question.
So can you give us some of the examples of network functions? And the second one is, if NF1 is down, see the expectation that network functions are all stateless, because on the request it went through NF1, but on the response, if NF1 is down, it will go to NF2. So how does it work? Because request went through one path and response came through another path.
Okay, so to the question one, so we so from the use case, our use case point of view, we have done this for to integrate with the external firewalls, right? Next gen firewalls. That's the use case. So
Layer 7 firewall.
layer 7 firewalls. And coming to the second question, yeah. So in case of uh, if something happens, right, NF1 goes down, so the connections has to be re-established unless the network functions itself are doing a session sync and all of that. Right. Yeah. Yeah.
If it is stateless,
Yeah. Yeah.
if it is stateful, it has to sync.
Like, yeah.
Okay. Thanks
Thank
a
you.
lot.